We're going to wrap up this introduction to congruence by thinking about two other geometric types of objects. The first are parallel lines, and how do we understand what it means for a pair of lines to be parallel. And then also we'll think about circles and the role that they play in thinking about congruence in geometry. First of all, since we're talking about congruence, which is a measurement of sameness, we're going to think of parallel lines as enjoying a sameness of direction. Parallel lines both go the same way, in a sense. But how do we make that notion more precise without having to use things like coordinates? If we were in the Cartesian coordinate system, we could say something like, well, two parallel lines have the same slope, for whatever that means. But we don't want to do that. We want as much as possible to do geometry in a coordinate-free way. So here's one way to think of what it means for two lines to be parallel. The set of lines on the top here, I'm going to think as being converging. If we were driving cars on each of these lines going from left to right, those cars would be getting closer together over time. If we continue those lines off to the right, there would be an intersection point between those two lines off at the right side of the page. Likewise, our set of lines at the bottom of the page we would think of as diverging. If I were driving cars from left to right, those cars would be getting further apart as time went on. And so to find an intersection point for that pair of lines, if we extend them going both ways, we would find that intersection point on the left side of the page. And so it's that tipping point in the middle between converging lines and diverging lines where we get parallelism. So how do we think about parallelism as a phenomenon we can measure? One way of doing it is by drawing a line that crosses both of our lines. So we call that a transversal. If I draw a transversal on a pair of converging lines, the example up here at the top, and if that transversal, for example, makes a right angle, 90 degrees, with one of my lines, then the angle it's going to make on the same side of that 90-degree angle on the other line is going to be smaller, less than 90 degrees. Likewise, for a diverging line, if I run a perpendicular transversal to one of my lines, then the angle that transversal makes with the other line on the same side will be greater than 90 degrees if we have a pair of diverging lines. And so one way of measuring parallelism is by drawing a perpendicular transversal to one line, and observing that it will also be a perpendicular transversal to the other, that angle on the same side as the right angle that the transversal makes is going to be equal to 90 degrees. And that's what happens with a pair of parallel lines. That's a way of measuring parallelism. And according to Euclidean postulates, a pair of parallel lines do not have an intersection point. So my converging lines had an intersection point on the same side as my pair of angles that I measured. My diverging pair of lines had an intersection point on the opposite side of the angles that I measured. And so my parallel lines, we postulate, will not have an intersection point at all. Two parallel lines, quote-unquote, never intersect. It's a postulate of Euclidean geometry called the parallel postulate. Okay, so is there a more analytical way to understand the difference between these three scenarios? Sure. Imagine what would happen if I switched up the roles a little bit. In my converging lines, instead of drawing a perpendicular transversal to the purple line, what if I did that to the green line instead, so my right angle is on top? Well, then my angle on the bottom is going to change to something less than 90 degrees. So in both cases, we have one right angle and one angle that's smaller, one acute angle, less than 90 degrees. Likewise, on my diverging lines, if I interchange where my right angle is, then my obtuse angle moves from one line to the other, and so I'm always going to get one right angle and one obtuse angle that my transversal makes on the same side. For my parallel lines, I'm getting right angles in both cases. But what we have here is something that physicists will often call a conserved quantity. If I call the angles that these transversals make with these pairs of lines alpha and beta, then if I play around with how my transversal is oriented, I should be able to see something about alpha and beta remain the same. In my parallel example, if I take my perpendicular transversal and I skew it a little bit, one of the angles it makes on the right-hand side is going to become obtuse, and the other one is going to become acute. And what we'd like to know is whether the amount by which one becomes obtuse is the same amount as the amount by which the other becomes acute. However many degrees we gain on the line on the top, we will have to lose in the angle that's on the bottom. And in fact, that is the case. That if I call those angles alpha and beta, then in the case of my converging lines on the top, the sum of alpha and beta, no matter how I draw my transversal, is going to be less than 180 degrees. For diverging lines on the bottom, the sum of my alpha and beta, no matter how I draw my transversal, is going to be greater than 180 degrees. And so one way of defining parallel lines is that I have a pair of lines such that any transversal that I draw that crosses both of those lines is going to create these two angles alpha and beta, and the sum of alpha and beta will be equal to 180 degrees no matter what. Whether it's 90 and 90 as in our original example here, or if I skew the line a little bit, then however many degrees one of those angles gains, the other one has to lose so that their sum remains 180 degrees. So there are ways of characterizing what it means for a pair of lines to be parallel that don't rely on extrinsic things like coordinates and slopes and the other things that you might be used to in algebra. It's only dealing with the measures of angles, and that's something we like in geometry. Finally, I want to think about the role that circles will play in our study of geometry, because they turn out to be a pretty recurring theme in the first portion of our course. As a reminder, what is a circle? It's the set of all points, P, which have a common distance to a given center point, a fixed center point that we might call C. That common distance is called the radius of the circle. So what will be the nature of our interchange between circles and triangles? Because we've made triangles kind of an important object for us so far. Well, any 3 points that I place on the circumference of a circle will determine for us a unique triangle. Unique, again, up to congruence, right? As long as those 3 points are not overlapping one with another. So if I just pick 3 points P, Q, and R on the circumference of a circle, and I can just connect them and get one and only one, up to congruence, triangle. So circles can determine triangles for us in that way. But what's more interesting and much less obvious is how triangles can in turn determine circles. So given a triangle, how do I determine a circle out of it? Well, it's a little bit of a surprise, it should be at least, that given any triangle, there is a unique circle that passes through all 3 of its vertices. We call that the circle circumscribed around that triangle. So it passes through all of that triangle's corner points, its vertices. But not only that, there's a second circle that instead of crossing all 3 of the vertices, will instead touch all 3 of the sides on the inside of the triangle, such that it's tangent to each of those 3 sides. We call that the inscribed triangle. So there are 2 different ways that a triangle can determine a circle, but neither one of those is obvious to us at this point. It's something that we'll take up in more detail in Chapter 2 when we talk about concurrency. So if the interchange between circles and triangles is a way of thinking about how to arrange 3 points along a circle, let's take a step back and look at some final definitions of what to do when we arrange points around a circle, beginning by thinking about 2 points. If I place 2 points P and Q on the circumference of a circle, those 2 points are going to determine for me what's called a subtended arc, the arc of the circle subtended by P and Q. Usually we're going to think of that as the shorter of the 2 arcs that joins P to Q, but from time to time we may think of it as the larger, the one that goes around the outside of the circle this way, rather than the one that's been labeled here. But they determine a subtended arc. They also determine, if I connect P to the center of the circle, C, and then to Q, they determine what we call a central angle. It's central because the center point of the circle is where we measure this angle. So 2 points on a circle will determine a subtended arc on the circle, as well as a central angle at the middle of the circle. And we can find an equation, a formula, that tells us how those 2 quantities are related one to another. If we throw a third point in there, as we do when we study triangles, then we can also define some additional quantities. If I throw an R on this circle, then instead of connecting P and Q to the center, as we did when we measured the central angle, we can instead connect P and Q to R, so that I have 3 points on the circumference of the circle being connected, and we get what's called an inscribed angle. And one of the more powerful theorems in this portion of the course is that theorem which relates the measure of an inscribed angle in a circle to the measure of the central angle in the circle. It's called Fales Theorem, and it's going to be really one of the more important engines behind a lot of the analysis that we do in Chapter 1. So for that reason, circles are going to be a really important and useful tool for us, even when doing things seemingly straightforward like studying congruence of triangles and other polygons in geometry.